Welcome to our second lecture on contour integration. Today we're actually going to do a contour integral. So over here on the board I've given us the definition from the end of the last lecture. Remember that a contour is a very nice curve. It's a finite sequence of smooth curves joined end to end. Remember, smooth means that the curves are differentiable and their derivative is never zero, so we never stop when we're drawing the curve. So the problem that we would like to solve today is we have a function f, which is a complex function. It's a function from the complex plane to the complex plane. And we have a contour, one of these nice curves. It takes a real closed interval into the complex plane, so it traces out a curve. And we'd like to integrate f along z. So in terms of a picture, there's our complex plane. And let's say that our curve starts here and goes up here. So this would be the point z of a. This would be z of b. Now f just kind of lives around here. Okay, and what we want to do is integrate f's values along this curve. Now, we're not going to get too in-depth about the Riemann sum version of this problem, but let's just think about it a little bit. Okay, so in ordinary calculus, remember, we're integrating a function. The integral is the area. We chop it up, so this would be like a x0, x1, etc. We chop it up into these little pieces, and then we sum the areas of these rectangles that we form. And we can form the rectangle either going, say, to the left or to the right. Okay, you've seen this. There are many ways to make these rectangles. And then we would sum their area. That would be the Riemann sum. And if our function is nice enough, we take the limit as the number of these little dividers that we put in goes to infinity, and that approaches the integral. Now over here, we want to integrate just along this curve. So we're going to chop this curve up a number of places. Okay. And now the question is, what does it mean to integrate along here? Now you've seen a very similar concept in multivariable calculus, so I just want to talk about that for a minute. You've seen line integrals. Okay. In this setup, your line integral in Calc 3 would be an integral along the curve C, which is parameterized in this case by z of f, and then we usually say ds. In Calc 3, we write the ds we mean by arc length, parameterized. Sorry, the integral is done with respect to arc length. And what that works out to be in the Riemann sum is that you're going to take your function at some point in each of these little pieces of the curve, and you're going to take a function value and you're going to multiply that by the length of that piece of the curve. And you're going to sum all those up, and it's going to take, you're going to take a limit, and it's going to go to this line integral. Now, in the case where our curve is parameterized by the function z, which maps from, or its bounds are a and b, this would become the integral from a to b of the function at the curve f of z of t. And now, where does the arc length come in? We have to multiply by the speed of the curve at each point. The speed is, remember, in this case it would be, I guess, the magnitude of the derivative. Okay, and we integrate with respect to t. Okay, that's the Calc 3 version of a line integral. Now, contour integrals are a little bit different, and the difference comes up right here. So, in Calc 3, we integrated with respect to arc length, but now we're going to integrate with respect to the actual change in z. So, our contour integral is going to look like an integral over a curve c of f of z with respect to z this time. That's the important difference. So, whereas up here in the Calc 3, we were taking the length of these little line segments, now we're going to say, let's take the change in z value in these little segments. Okay, well, what that works out to be, if you work through the Riemann sum, we'll integrate from a to b of the function at the curve times, instead of the speed of the curve, it's just the derivative of the curve. That's how much z is changing. So this is our definition of the contour integral. Now let me note that in Calc 1, the integral can be interpreted as an area, which is very nice in terms of just thinking about its properties and things. The contour integrals don't really have such a nice interpretation in terms of like an area. And they're not exactly like the line integrals we've seen from Calc 3. Okay, before we do one, let's talk about what conditions we would need for this integral to exist. And this is a bit of overkill, but when will this integral exist? If f evaluated at our curve is nice. And why is that true? That's because we already know that this z prime is nice. It exists. That's the part about the curve being smooth. Okay, so what do we need out of this? Well, it's certainly fine if it's piecewise continuous. Okay? That's really massive overkill, but it'll work. And basically all of our examples will be like that. So just be careful, certainly you can't integrate over, say, a singularity of f. All right. So let me erase this side of the board, and then we'll... All right, we are ready for our very first example of a contour integral. Okay, let's integrate the function 1 over z along the contour c, where c is going to be the unit circle Now remember, all of our curves are oriented, so I have to tell you which way we're going around. I don't think we got into this last time, or we just didn't mention this word last time. We're going to call positive the counterclockwise orientation. So this is positive orientation And by that, I mean counterclockwise. Okay. Well, we look over here at our rule for the contour integral. We're going to have to plug the parameterization of the curve into the function, then multiply by the derivative of the curve. So first we need to find our z, so parameterize the curve. This one's easy, right? We're going to just parameterize it as e to the I theta. So z of theta will be e to the I theta. Okay, and theta will run from 0 to 2 pi. That's parameterizing our unit circle in the positive counterclockwise orientation. Next, we're going to need the derivative. Well, that's easy enough. We know how to take the derivative of z, the derivative with respect to theta, the parameter. The I comes down, and we get e to the I theta. Okay? Third, well, we're just going to plug in and see what we get. So our integral is the integral from 0 to 2 pi. Okay, 1 over z, well, z is e to the I theta. So that is 1 over e to the I theta times the derivative of z. Well, the derivative is I e to the I theta, and then we integrate with respect to our parameter theta. Okay, we have this great cancellation here. So all we're doing is integrating I, and I is just a constant. Well, we integrate a constant over a range, and we get 2 pi I. Okay, so now let's play with this for a little bit. What if instead of going around the circle once, we wanted to go around the circle, say, 3 times? What would change? Well, last time we talked about 2 different ways to parameterize going around the circle 3 times. One of them would be to just let our theta go all the way up to 6 pi. If we were to do that, then just the upper bound of our integral would be 6 pi. So we'd be integrating from 0 to 6 pi I, and we would get 6 pi I, which is 3 times the contour integral when we went around once. Okay, the other way is we said we could do an e to the 3I theta, in which case the derivative would be 3I e to the I 3 theta. And the e's would still cancel, but now we'd be integrating 3I from 0 to 2 pi, so we'd get 6 pi I. Okay. So that's one variation. What if instead of the positive orientation, we took the negative orientation? So instead of going around counterclockwise, we went around clockwise. Okay? Well, one way to do that, remember last time we talked about a general way to reverse orientation. And in this specific case, there's just a nicer way to reverse the orientation. We just put a negative in there. Okay, that'll start when theta is 0, and it'll go that way. And it'll end when theta is negative 2 pi back back at the point 1. Well, if we do that, then our derivative becomes minus e to the minus I theta. And then we'll put the negative in here, the negative in there. There's a negative because of the derivative. The e's cancel. We're integrating negative I, and we get a negative 2 pi I. Okay, that's just like how in single variable calculus, the integral from a to b is the negative of the integral going the other way, from b to a. So if we reverse the orientation of the contour, we'll get the negative of the contour integral. And we'll see that more generally here in a moment. Okay, what if instead of the entire circle, we just wanted to go from 1 to minus 1? So let me erase this board so we have some room to do this. All right. Now, we're going to go from 1 to minus 1 along the unit circle. You know what? Let's go from minus 1 to 1. That seems like the proper way to go. If we go along the top half of the circle, the top hemisphere, what do we get? Well, first we have to think about how we're going to parameterize this. We still want to use, well, let's see, this is going in the clockwise orientation, so let's use e to the minus I theta. And what do we want theta to do? We could start it at minus pi and go to 0. Okay? Now, our derivative is going to be as it was over here, minus I e to the minus I theta. And so we're going to plug in, and we can just jump to this. So here is our new curve. Let's give this a different name. C1, 1 over z dz. Okay, we're going to get the integral from minus pi to 0 of minus 1 over e to the minus I theta times I e to the I theta. Remember, the minus appears from the derivative. Really should be over there. D theta, everything cancels except for a minus I. And then we're integrating from minus pi to 0. That is a range of pi. So we get minus I pi. Okay, there's no reason why it should be exactly half of this that we've noted at least, but it is. Now, what if instead we went along the lower hemisphere? Okay. Now you'll notice we're still going left to right, but it became counterclockwise. So here, we would like to use our normal parameterization. And what should theta do? We could think about it as going from pi to 2 pi if we want. And we'll call this curve C2. And we will integrate 1 over z over C2 with respect to z. Pi to 2 pi of f of z times z prime. In z prime, the I comes down. Okay, again, the e's cancel. We're integrating the constant I from pi to 2 pi. So we get pi I. So the important thing to notice here these two answers are not the same. In fact, they're opposites of each other, even though we're integrating, in both cases, from -1 to 1. So now if you remember back to Calculus 3, we studied certain kinds of vector fields where the path didn't matter. So in the case of contour integrals, for right now, all we know is that sometimes the path matters. So in this example, the path we took from -1 to 1 did matter. Okay, let's erase this side of the board now. In fact, I think we can erase all of the board, and we're going to do another example. Okay, so what we just saw was that when we were integrating the function 1 over z from -1 to 1, the path mattered. In our next example, well, let me just write it down. We want to integrate the function z with respect to z along C, the curve C, where C is any smooth curve. Parameterized by, well, our standard curve parameterization. Now, our last example should make you ask, well, why would we do this when we know that the integral can depend on the curve? Well, precisely in this case, the integral will not depend on the curve, as we'll see. And so the question is, what is different about this integral and our last integral? Okay. Now, clearly the only way we're going to solve this is with a cute trick. We don't know enough about the curve to actually integrate anything, really, do we? Let's write out what the integral is. We're asked to integrate z, and we know that we'll be integrating from a to b of our curve z times its derivative. Now, we stare at this thing. We're going to just solve this problem today in a very ad hoc manner. But it should suggest to you that there might be some more general principles that might be coming later. So we look at z times z prime. Now, I'm going to go backwards here. Sorry about all the parentheses there. What is the derivative with respect to t of the function z squared? Okay, well, by the chain rule, the 2 comes down. We get a z of t times its derivative. this is twice what we're integrating right up there. So what does that mean? Well, the integral we want to do, which is the integral from a to b of z of t, z prime of t, okay, that is 1/2 of this derivative. The integrand is 1/2 of that derivative. I'll write it that way this time. Now, we know that, of course, the constant comes out, and then we're integrating a derivative. So by the fundamental theorem of calculus, those two things undo themselves. So we end up with z of t all squared evaluated between b and a, with the constant 1/2, which I almost forgot. Well, so this is z of b squared over 2 minus z of a squared over 2. So it didn't matter at all how z went from a to b. All that matters are the endpoints, z of a and z of b. So here, unlike our previous example, we have path independence. The value of the contour integral is the same no matter how we went from z of a to z of b. The other thing that this hints at, and it hints at it right over here, is antiderivatives. Okay, so what we said is that the derivative of z squared is 2z prime. So that means the antiderivative of z times z prime is z squared. Okay, that is something that we're going to further develop in future lectures. Okay, next we will clean off the boards one last time and look at some relatively boring properties of contour integrals. Okay, two boring properties of contour integrals. The first one is, just like with all of the other kinds of integrals, these things are linear operators. So when we integrate a sum, that is the sum of the integrals. Notice, we don't even need really to write a proof of this. If you just took this integral and expressed it in terms of its definition, f of z plus g of z of t all times z prime of t, and then it's expanded out, and then it's not a contour integral anymore, and then this follows immediately. Okay, the other boring property, although not quite as boring. Let's say we have two curves C and D, and let's say that they actually do, C ends where D begins. Then I'm going to write C plus D to mean go around C and then go along D. This is the same as integrating along C plus than integrating along d. That's why a little while ago when we went 3 times around the circle integrating 1 over z, we got 6 pi, because we could write that as just c plus c plus c, and we're getting 2 pi I, and another 2 pi I. Okay, those are the boring properties. Slightly more interesting is, what if we have a curve C and we want to go around it in the opposite orientation? Now, if you think back again to our first example, we did this. When we went around it in the counterclockwise orientation, we got 2 pi I. When we went around it in the counterclockwise orientation, the clockwise orientation, we got negative 2 pi I. So the question is it always true that if you go around in the negative orientation, you get the negative of the integral? And it is true. So let's say we've got a curve C. The negative of C we will denote by minus C. So minus C goes through exactly the same points as C, just in the opposite direction. Now, let's say that C is parameterized by Z, which is our standard curve with endpoints A and B. Then how do we parameterize minus C? Well, we talked about this in the last lecture. We plug in minus t, so we look at z of minus t, and then where does t lie? It goes from minus b to minus a. Okay, again, remember, in the circle case, we have a nicer way to write this, but in the general case, we have to do this, where we make everything negative and these two get flipped. Okay, so now we can think about taking the contour integral of f along minus c. Okay, along minus c, we go from minus b to minus a. F of the curve, well, the curve is z of minus t, okay, times the derivative of the curve. Well, I'll just write it in as the derivative for this step. In the next step, we'll take the derivative. And how do we take that derivative? Well, this is just the chain rule, right? We have a minus t inside the function z. So a minus is going to come out. Let me bring that minus all the way to the front of the integral. It'll go right there. And then we will have the derivative at minus t. Okay. This is, notice the difference here. Here I'm saying the derivative of z of minus t. Here I'm saying the derivative of z evaluated at minus t. Okay. Now, we've got all these minus t's around. Where are they? There and there. So we're going to just make a substitution for the minus t. That substitution is going to cancel this negative sign out front, so it will disappear. And then remember, since we're doing a definite integral, we have to apply the substitution to our bounds as well. So the bounds will turn into a positive b and a positive a. Okay. I guess we'll use u as our substitution variable. Okay, and what is this integral? Well, if we ignore the bounds for a moment, f at the curve, the normal curve, the z curve, okay, so that's the normal parameter, that's the positive orientation of c times the derivative of z. Okay, so this is all the integrand from the contour integral of f over c, but the bounds are flipped. Instead of going from a to b, we go from b to a. Well, we know from calculus that flipping those bounds just introduces a negative sign. So indeed, we get the negative of the integral of f along c. Okay, so that is our first real lecture on doing these integrals. And our next lecture, we're going to look at more examples of these integrals. We're going to be doing this for several more lectures now.